As I said, I'm going to spend the rest of this introduction talking about the simulations that we are going to do. But before we start, why do we do simulations in the first place? Number one reason, it is fun. I know what you're thinking. Every time some teacher said it's going to be fun, it was never fun, right? So let's see if it is the case here. I'm at this physics education technology site at University of Colorado. And you can come to the same site as I did by typing this in here. I'd like to show you one here. We can actually do a simulation of the solar system. When I click here, this opens up, and I'm going to have another body. So presumably this is the sun, the earth, and the moon, but not really because the masses are not in the right, correct ratio. But still you can see what happens here. When I run this, it goes around, it orbits. So let's run it for one earth year. There we go. So this is what happened here. Now here you can learn a lot of things here. You thought the moon was going around in a circle, but there's nothing circle about this here. You thought the sun was standing in the sun at the center and the earth was going around. No, sun also orbits because of the earth and other planets. They push and pull. So we can learn a lot about physics, gravity, and action and reaction and other things by doing this simulation here. I will explain in more details in my class. Now, let's go back to the other one. So we could do other things here. I'd like to show you one more here. So this is about the energy conservation. So let's run this. Open. You can let this poor guy swing back and forth, or you can just raise the floor and see what happens to the guy, or lower it, or you can add more tracks to it. For example, like this here. And you can do such things as have him go around and gain the potential energy with this Earth speed, and then suddenly drop the gravity to zero so that the guy flies off. This is fun, but it's just not fun here. This is teaching the conservation of energy and how the gravity works in producing different speeds at different heights. So in my class, you will learn how all this physics, the physics behind all these interesting looking animations, and we are going to understand how the universe works in a deeper level. The second reason we use simulations is, one, it could be impossible to do, as in this one here, I will explain, or it's too dangerous, such as global warming. We cannot wait and see what happens when the temperature goes up and say, hey, we are toast. It's too late then, right? So let me show you this one here. First of all, this is Mathematica. Take a look. You have 5 lines of code. Well, this is not even a line here. So you got 4 lines of code and you can do this simulation here. What is this? This is about drilling through the earth. What if you cut through the earth here and you dropped something through that tunnel? And assuming that the tunnel is vacuum here, what would this object do in that tunnel? Would it go and get stuck or go all the way? Or what? You can actually find out. Run the simulation here. Ready? Okay. Run it. It goes back and forth. How do you know? Well, we simulated it. What if we cut through in a shallow surface like that? It's not even shallow. Actually, if you drew the Himalayas mountain here on this circle, in scale, it's not even a bump. So this is an impossible depth. We cannot do this. Engineering is impossible. So let's go. It moves like that. Okay, I will end it here. Now, what if I dug deeper through the center of the earth? What would happen there? We'll find out that it does this. That's very interesting. Okay, so that's the reason, another reason we are doing simulations here. You could not do this. The deepest drill that we drilled to extract oil is not even a dent in this scale here. Another reason we do simulation is for the visualization. We cannot see it with our own eyes, so we can do the simulation to visualize it. Here's a good example here, but I want you to notice how short the code is. Okay, so in here, this is timpani drums. So when you play it on the fundamental frequency, it just goes up and down like that. That would be something like doom sound, right? You hit the middle with something, a dull instrument, then it goes through this motion here. But this is not the only motion it's capable of going through. So let me show you here. I will show this here. It can go into harmonics of different. Let me show you. It looks like this. So it could vibrate like this. Of course, in reality, it doesn't go up and down like that here, but it will do it in that small scale here. So now you get to see here, and you get to explore other modalities of timpani. So this timpani, if you play it by putting your hand or finger on certain parts here, you can force this kind of oscillations. So it produces different pitches depending on how you do it. So here it is. So this is possible. And it can go on like that. But after that, the volume gets pretty low. Those who play string instruments, you know how harmonics works here, right? That's exactly how it works on the drums. And there's also this harmonics on the other side in the radial direction. So this could happen. And you can have different pitches as a result here. But the thing is, this mode and this mode can be mixed. So you can have all kinds here. I'm not sure to what extent you can actually make it happen in physical timpani set here, but in visualization and simulation, we get to see what is theoretically possible. So once we explore this here, then you go to the actual instrument and see if you can reproduce this to validate or to invalidate your theory.